Today, we're diving into something called Cramer's rule. It's this incredible place where a puzzle in algebra gets its answer from the world of geometry. We're going to see how a concept like volume can actually be used to solve for unknown variables in an equation. It's pretty wild.
So, it all kicks off with a question that honestly sounds a bit like a magic trick. How is it possible that one single number, pulled from a whole grid of other numbers, can tell you for sure whether a system of equations even has a unique solution? That's the mystery we're going to unravel.
At its core, we're just talking about something most of us have seen before, a system of linear equations. You've got a couple of unknowns, like x and y, and a few equations that tie them together. The whole goal is to find that one specific value for x and that one specific value for y that makes all the equations true at the same time.
Okay, now here is where it starts to get really cool. The secret to cracking this algebra puzzle doesn't actually come from more algebra. Nope, it comes from geometry. Specifically, this idea of area, or in 3D, volume. And the key that unlocks it all is a concept called the determinant. So the determinant, it's just a single number that you calculate from that grid of numbers in our equations, which is called a matrix. But here's the trick. Don't think of that matrix as just a boring table of numbers. Think of it as a set of instructions for a geometric transformation, and the determinant is the key to understanding what that transformation actually does.
So imagine our matrix tells space how to stretch or squish or rotate. The determinant tells us exactly by how much. It's a scaling factor. So a determinant of 2 means all the areas in your 2D space just doubled. A determinant of 0.5 means they all got cut in half. It's that simple.
Now, the absolute make or break difference here is whether that determinant is 0 or not. If it's anything other than 0, the transformation keeps the dimensions of space. A 2D area stays a 2D area. But if the determinant is exactly 0, well, the transformation squashes everything flat. It collapses 3D space into a 2D plane, or a 2D plane into a 1D line. And a 0 determinant is a total deal breaker for finding one unique solution. I mean, think about it. If you've squashed a 3D cube down into a flat 2D square, you've literally lost an entire dimension of information. A whole bunch of different points from that original cube are now all sitting on the exact same spot. There's no way to reliably unsquash it because that information is gone forever. That means the transformation isn't invertible, and that's why there can't be a single unique solution. So, this whole geometric insight is our key. If the volume of our system isn't 0, we know a unique solution exists. But Cramer's rule is even cooler than that. It doesn't just tell us if a solution exists, it uses this very idea of volume to find the solution itself. And this leads us right to the big aha moment. It's one thing to know that, yeah, okay, a solution is out there, but how in the world can we use this geometric concept of volume to figure out the actual numerical values for x, y, or z? And this is the beauty of it. The solution for any variable turns out to be just a simple ratio of these volumes. First, you calculate the determinant of your main matrix of numbers. Let's call that the total volume of the system. Then, say you want to find x. You make a new matrix by swapping out the column for x with the answer column from your equations. You calculate the volume or determinant of that new matrix, and the value for x is just the ratio of those two, the new volume divided by the total system volume. That's it.
The theory is really elegant, but let's make this real. Seeing how this works with actual numbers is what's going to make it all click into place.
So here's the rule in its formal algebraic glory. For any variable, its value is the determinant of a slightly modified matrix divided by the determinant of the original one. What might have looked like a scary, abstract formula before, now, well, it just looks like the volume of a part divided by the volume of the whole.
Okay, let's put it to the test. Here's our system. The matrix of coefficients, A, has a determinant, its base area, if you will, of -42. Now, to solve for x, notice what we do. We take that first column, the one for x, and replace it with our answers, 15 and 13. This new matrix, A sub x, has a determinant of -84. Then we do the same for y, swap the second column, and we get the matrix A sub y with a determinant of 126.
Now, we just apply the rule. The value of x is the determinant of ax divided by the determinant of a. So that's -84 divided by -42, which gives us a nice, clean 2.
And for ay, you guessed it, we follow the exact same logic. The determinant of ay, which is 126,
divided by our system determinant, -42, gives us -3. And just like that, we have our unique solution. X equals 2 and y equals -3. So if this rule is so elegant, why don't we use it for absolutely everything? Well, it turns out its true value isn't always about being the fastest tool for the job.
Look, Cramer's rule is absolutely brilliant for understanding the theory. And for solving small 2x2 or 3x3 systems by hand, it's great. But the number of calculations you have to do just explodes as the matrices get bigger. For the massive complex systems used in science and engineering, computers use way faster methods, like Gaussian elimination.
And this incredible idea wasn't the work of just one person. It has this really rich history. While Gabriel Cramer gets his name on the rule for publishing it in 1750, mathematicians in Japan and Scotland were already playing with very similar concepts decades before. So really, the ultimate value of Cramer's rule isn't about being a calculator. It's about understanding. It's a conceptual bridge. It is beautiful, definitive proof that an abstract puzzle about numbers can be completely reframed and solved by asking a very physical, intuitive question about geometry. And that really makes you wonder, doesn't it? A matrix isn't just a grid of numbers. It's this compact, elegant description of a geometric action, hiding concepts like volume, orientation, and so much more. Which leaves us with the big question. What other secrets are hidden inside a simple matrix?